Good afternoon, everyone. Thank you for joining this fourth technical session. And our topic today will be on the Depogrid modeling and simulation. So this is a continuation, of course, of the reservoir engineer technical session covering all the countries on the Sub-Saharan Africa region. So glad to have you in this call. So please, if you have any questions, just type in the box. We will try to answer. My colleagues who are sharing the session with me, we will answer them as we go through the presentation. Otherwise, you can also wait until the end and we can have an open discussion on any specific section from this presentation and the demo, of course. Okay, so today you have myself and Samuel Aderemi. So we are the ones that will present to you. I'll do the main presentation slides and Samuel will cover the demo for us. So Samuel is a reservoir engineer technical lead. So he's the lead on all the technical solutions and site and service provider. So we are glad to be with you today. And following on to our agenda. So our agenda today will focus, mainly speaking, on the reservoir characterization in main and varied deposition environments across the main, GNG and RE. A little bit of a summary of the integrated workflows we have from the geological model all the way to the reservoir engineer model. And then we'll focus on the Depogrid. We will tell you in detail what is it, why is that important to use it if required, some detailed specifications of its concept, the workflow in Petrel in order to build this grid, and following by a live demo where you can see hands-on how we can quickly build the grid and QC it as well, quality check. Okay, so we know that characterizing the reservoir, especially looking on the geological side, can be a challenge because we have to account for its depositional features, for the geology itself. What is the structure of a reservoir? And looking to the different geological environments, we have different general complexities. One is the stratigraphic, leading to the main deposition features you have, and the other one is structure, which is doing to post-deposition events that can impact and alter our reservoir in terms of its structure. And that can be very, very, very complex. So, and we have all different type of reservoirs across the world. And in this picture here, you can see some of the some of the outcrops where you have, for example, please, can you mute your phone? I think I'm hearing some back noise. Hello. I think it's okay now. Okay, so I will continue. So if you look here on the picture in your left-hand side, it's just a summary of different structural events you can have within your reservoir. For example, compressional events where you have thrust faults, which also impacts your reservoir in terms of flow pathway. And then you have extensional regimes. Apologies, can you please just mute your phone so that we don't have back noise? Sofian, please, can you help in muting?
Yeah, go ahead. Yeah.
Thank you. All right. So then we have the extensional regimes, which are mainly leading and characterized by normal faults. And here you have example of different outcrops where we can clearly see the fault planes and the movements we had across the different sides of the fault, the footwall and the hand wall. So this is actually realistic representation of the reservoir structure we have in the subsurface. So these structures impacts most of our reservoir today. But not only look into the structure itself, which are post-depositional. If you look on the right-hand side, we have stratigraphic complexities. Some of them are the cross-bedded reservoirs, and here you have a picture from US Utah where you have big cross-bedded. Those are especially characteristic when you have fluvial deposition or turbidate fan deposition. So a lot of crossbeds where we have our main channels. So this will be the section of our main core reservoir. And below as well, image from Utah, we have a more 3D view of how complex these structures can be. And here we are looking also to cross-depositional beddings, mostly looking to an aeolian deposition environment. So these geological complexities will greatly impact our reservoir dynamics, especially not only counting to volume, but looking into flow, fluid flow, oil, water, gas, especially when you have high permeability layers, which can quickly push the water from your aquifer or from your injector out the way to the producer. So it's very important we are able to characterize our reservoir and be able to have the most representative as possible these features that characterize our geological model. So because of that, characterizing the structural and stratigraphic complexities we have in a reservoir has always been taken into account as we are modeling in detail by our GG team. And especially when we have uncertainties we want to deal in history match, as I was mentioning before. If you want to match your water breakthrough, if you want to match your hypermeability layers, especially you remember from our previous session, we're talking about geoscreening, multiple realization of your reservoir when it comes to different channels and probabilities. So if we have agreed that does not allow us to represent this feature and being able to represent them without having simulation challenge, such as pinch outs we have, which then can lead us to a lot of convergence problems when we are simulating, which will lead to increased simulation time. So what we want to do is be able to model these structures with accuracy, but at the same time be able to model them and be able to reduce the convergence problem you may have in complex structural zones and stratigraphic zones, and also reduce the simulation time. If we're able to do that, then of course we're able to handle with more leanness the uncertainty problems we may have, which will lead on the history match. So all of it is linked, is integrated. And today we want to show you how are we able to better handle the grid to account for these geological features and also to account for simulation features in order to address uncertainties we have in the subsurface. So there are two main common, most used type of grids across the industry using Petrel. One of it is the pillar grid, which I will explain all of them in detail, which are mainly based into pillars. You see here on the left-hand side. One very good characteristic of this grid is that you are able to preserve and having the main representation of your faults. Although you have a lot of cells which will not be orthogonal, and of course will give us convergence problems as we are simulating. Then we have the other type of grid, which we call the stair-step grid, which is a volume-based grid, where in order to be able to represent better the reservoir, but not have the convergence problems when we are characterizing a fault, and to be able to better characterize complex faulted structural, heavily impact structural grids. The stair-step grids allows us to do that with accuracy, but of course, in terms of the fault surface, fault volumes, those are zigzag faults. So those are the two main common use grids today. And the third grid, which is the grid we want to present you through this section, is the Depogrid. So here you can see in the bottom, so the Depogrid ended up to be a combination of the pillar grid method and the stair-step grid method using VBM combined in one. So in this grid, I'm able to keep the faults on this detail to better simulate them. I can handle the cells which are not which are angular, because these cells will be orthogonal, and I'll explain why. And also I'm able to preserve the deposition space. So the Depogrid is a combination of both pillar grid and stair-step grid in terms of workflow, and give us a more detailed accuracy when we want to represent those complex features I was showing before. Now here is the detailed workflow going from the static model to dynamic model when we want to build the grid. It's a little bit busy, but I'll just spend a few time so that you can understand it. So our GNG team, colleagues, so we'll start by modeling out the surface, out the subsurface from the seismic interpretation, build the fault domain framework, and if using a stair-step grid, build the VBM model. So if I have a pillar grid, the normal workflow will be from the seismic interpretation, I will pick up the main horizons, and from that, I will create the pillar grid model, characterizing, taking into account the faults, and I will create the pillar grid. From this pillar grid, I can then start model my properties, porosity, permeability, net growth, and through that, continue with the workflow to simulation, PVT, scow, adding the wells, the controls of these wells, and then we can run the simulation using Eclipse or Intercept. If I want to build a stair-step grid, what I have to do is comparing with what I did before in the pillar grid, I have to create the fault framework and the structural VBM model, and through that I will having the stair-step grid. As I was showing before in the picture, is a grid that allows us to have the faults in zigzag, and also allows us to have a better representation of the deposition space. I'll get there. So once the stair-step grid is created, then again we will populate our petrophysical properties, our phases model, and through that we'll go continue the workflow into the simulation. Now, with the new grid, which is Depogrid, we add in an additional step into the normal workflows. And the Depogrid is, I'll say, is more based and aligned to the stair-step grid. So the workflow we have to do in order to build a Depogrid model will be from the seismic interpretation. We need to have the fault framework created, the structural model with the VBM, and we go to the Depo space. So in the Depo space is where we will populate our properties, our geological properties. I will explain that soon. And after we having the Depogrid created. So it's a grid, as you can see, I can preserve, align the faults, but also I can preserve very well the main orthogonality of the cells. So once the Depogrid is created, we can populate our properties, petrophysical properties, and then continue the workflow to simulation. Although there is one specific point here when we look into the Depogrid, is that is only handled today. There is only one simulator that can handle this grid, which is intercept. And that is because the Depogrid is an unstructured grid, a Pepe grid, which is a port bilinear bisector. So this means very few simulators are able to handle unstructured grids, unstructured cells, and Intercept is the only simulator in the market that can handle that today. So I will show you also in more details how is the workflow to run the Depogrid model. So here are just some detailed specification. I'll just summarize for you. So the pillar gridding, one of its main point is that is able to represent your fault planes accurately, although give you some challenge on the main cell's orthogonality, which leads to the main simulation challenge. The stair-step grid, which is the second one, allows us to better represent the position feature, but of course compromise the fault. And the Depogrid is the one that combines both. And this is the integrity I was telling you before. So we are able to represent better the faults. We are able to have a robust accuracy of the deposition system, and we can accommodate on the simulation part because we have less convergence, less challenge when we are simulated. Okay, so now let's see, what is the Depogrid indeed? So the Depogrid is a cut cell grid which is done through the Depo cells, okay? And one very important thing is that the pillars of this grid are directly orthogonal to its stratigraphy. So the Depogrid is aligned to the sequence of the position of your model, okay? So if you have a very complex fault system, like you see here, so all your faults and the fault planes, so all of them will be leading and created by cut cells. So what you see here across the fault plane, you have your cells automatically cut. But since this is a structural grid, that will not create a problem because we don't need to have them orthogonally when it comes to the angle. So, but make us accurate when we are counting for volumes across one side and the other side of the fault, and also the main transmissibility across the fault plane. There's another very important feature of the Depogrid, and this one is the Depo space, which I'll explain you soon. So the Depo space, what it allows us to do is, in order for me to populate my properties, my channels, I have to do it in the real deposition environment and not take into account the structural impact it had when the faults came in or the faults came in. So if you look to this picture, this is the present reservoir day when it has, which has been faulted. But you can see if we have layers and we have a structural movement, I will have superposition of different geological features across the fault plane. So when I'm modeling, if I'm not able to account for the fault movements and the unconformity zones, I may have challenge when distributing property with accuracy across one side of the fault and the other if I don't have input data. So what the Depo space allows us to do is to be able to model the phases, the fluvial system, and the properties in the real deposition system before any structural event was created. And then we can go back into the real structural event, and the same cells will have the same value. So that means it will be more accurate to model the properties, the channels continuation across one side of the fault and the other, and account for each movement across. Now, the question is, where and which fields, which challenges can the Depogrid model give value to my reservoir characterization? And the quick answer is, If you have reservoirs which are highly faulted or have stuck reservoirs, so Depogrid is really valuable for you to better characterize your reservoir. Also, if you have compressional regimes such as thrust faults or faults within your reservoir model, then Depogrid it is the way to go. And if you have stratigraphic complexities, which most of our reservoirs have within Africa, from the deltaic depositional features, the turbidite fines reservoirs which we have in, which has a lot of stratigraphic complexities. So Depogrid also will allow you to better model those features, and I'll show you some examples as we go through. So here is a detailed example of some of the deposition features that pillar grading or VBM can struggle a little bit to represent, from the manifolds, from the different foldings and folding, from complex sequence stratigraphy features, okay?
Sorry, what is VBM?
So VBM is volume-based modeling, which is apologies, I use a lot of acronyms. Thank you. So it's volume-based model, which is used to create both the step grid is one of the steps, and the Depogrid. So it's a volume-based model. So it's part of the workflow I was planning before.
Thank you.
Yes. Okay, so now I wanted to show you the detail and the value to add in the Depo space as part of our geological modeling when we are characterizing our reservoir features. So here on the left side, we have in the nomenclature. So geospace is the current present day depositional structure that our reservoir have, take into account all the faultings and folding that it may occur throughout the time. But for us to better model the continuity of our geological features, channels, and so on across the faults, it's easier and better to do it at the time it was deposited on the Depo space. And this is where and why we call the Depo space. So this you'll be hearing a lot throughout this presentation. I'll just repeat again. The Depo space is the original depositional space where the main you have the sediment happen of your reservoir, where you have the real connectivity of your channels preserved, and the geospace is the present reservoir structure, taking into account our complex structural events that happen. Okay, so we see our reservoir when we have seismic, when we interpret the cross-section and we characterize. We see our main reservoir in the geospace characterized here. But if we want to really understand the continuity and the connectivity across the reservoir, it will be easier to characterize its deposition features if we put them in the deposition space. And here we will be able to understand across the faults what is actually the relationship between one side and the other side of the fault, and that will not compromising our model and the continuity of the geological features across the faults, and of course for us in the simulation, the connectivity we have across the faults. Okay, and there are a lot of differences when we are looking to the geospace and to the Depo space. For example, if we have a compressional regime where we have folded system, and we see something like this today, it's very crucial we are understanding the real connectivity and the length of each deposition feature across the fault and across the folding. So the deposition space will allow us to better model with accuracy, and then we can revert back to the real presence in the reservoir. So this will allow us, number one, to preserve continuity across the fault plane and accuracy of the geological modeling. And what Depogrid will additionally do it is to preserve as well the full fault surface without having impact into the simulation. Now, also, by being able to distribute our properties in the Depo space, give us a big value because we will not be restricted and impacted by, please, can you please mute so that we don't have some back noise? Thank you. So if we use the Depo space as we model, we won't have some characterization challenges and misdefinition of a channel that may happen when we use pillar grading. So if you see here, top view, you have a grid which is faulted, and you have the fault pillars here, and you have the distribution of the channel taking into account the present day fault feature. And on your right-hand side, you have the channel characterization done in the Depo space, and then put it back with its structural movement. So with that, we can better characterize our reservoir. We can better characterize the real positional and continuity of our channel, and we won't have some errors that may occur if we try to model it, take into account the present day structure. So this gives us more robustness when we are defining the grid. And in the Depo space is a space where we have a specific orientation of our cells. So normally we are used to X, Y, Z and IJK, especially for us in simulation. But now in the deposition space, we use the UVW, which are mainly the main orthogonal direction. And this is what will be kept, especially when we are calculating the permeability value, which of course is directional and has to be aligned with the permeability tensor with direction of flow. So with that, we have a better representation of the permeability definition because we are doing that without having the impact of the structural effect when we are modeling our specific geological feature. Now, how does the workflow works to create the Depogrid? So first, we start with the real depositional present geospace, where we have faults and folds. Next step, what we do after the structural model is we are gonna flatten it in order to create the depositional space and align it without having the faults and the faults impact. And once we have the Depo space created, which is having this orthogonal grid, UVW, so that means our cells now will be directly orthogonal, taking into account the positional sequence we are looking at. After we have that done, we are able to distribute our faces and our petrophysical properties with accuracy, with more certainty in the depositional space. And after that, we will revert back to the present day depositional feature, which is the Depo space. We will preserve the depositional integrity and also the present day structure. So this is the general 3 major step workflow we are used to create the Depogrid. Now, looking into Petrel, and this is what you see in the demo we do it. So this is the tab within your structural framework, where you're having the steps normally starting from left to right, which will be used to create the Depogrid, starting by the fault modeling, then the model construction, which is the VBM, the volume-based modeling for the stratigraphic function. Then we're creating the zones, which will characterize our different sections of the reservoir. Then we move in and do the Depo space calculation, which we're able to put in from the geospace to the Depo space and distribute the properties after after we have completed. So it's the same cycle I've shown you before, and you'll be able to do that in Petrel following the steps you have here as we have characterized. Now, in the deposition space calculation, where we do the conversion of the geo space to the depo space, after we have done all the structural framework and all the model refining, here you see the geomechanical mesh deformation that is present today, and how does it look when we move into the depo space. So it's all linear according to the deposition feature we have. And also preserving the faults planes we have in a model, okay? And this is the value that Depogrid will give. So being in the depo space as we are, we can then populate our channels, fluvial plains, they'll take the position features, aeolian environment. So depending on which deposition environment you have, we will be able to model them accurately in the depo space without having to be take into account the structural impact. And then we revert back in the structural model calculation, then we can see in the real geological space, how does it look? So we have a grid, if you look here, that is geological representative, because we are certain, or we are more certain here, because we model physical parameters in the depo space, but is also accurate in the faults that we have here. So we don't need to have zigzag faults that we have in the same way that was used in the stair-step modeling. We have the normal pillars, the normal fault plane preserved, and being this grid and structure, we're able to simulate it without having problems of conversions within the fault zones or in the main complex structural zones. Okay, and here we keep the integrity of the grid. Of course, as we do in grid, we have to make sure we do quality checks, and this is a very important step when we're doing quality checks in a model. But one very nice thing that we're able to see in the Depogrid, which is challenged to see in the normal grid, is the normal outcrop surface boundary of each formation. That means because I don't have all my cells converging to a pillar, they will be able to outcrop in the surface, and we're able to see that in the Depogrid. We show you an example as we go to the demo, and we can be able to have our real representation of the surface of the subsurface location and movements, for example, folding if you have in a model. This is what we preserve. And of course, if you have cells that are having very high angle, very high depo space, we can correct it. But this is what allows us today to model a complete structural basin without having problems with the faults and without having problems with its facies integration across the structural impact. Okay. Now, one very important thing, when we are in the depo space, as I was mentioned before, we have a new coordinate, which is UVW, and this is what will be used for us in the simulator by Intercept to calculate the permeability tensor, which is, of course, directional. And once we move our model back to the geospace, it is preserved. So that means the Depogrid will not have an IJK orientation. It will have a VW orientation for the permeability calculation. Intercept will be able to handle that, and I'll show you in the next slide. Okay. Now, by being able to implement this workflow I just mentioned, we're able to characterize all of these features I have shown you here. And now I want to show you quick examples of it. Now, look into the compressional regimes, all the foldings, all the thrust folds we have, all the zigzags that we have within cells. With normal pillar grading, is challenged to keep and model a cell that does a U shape and go back up, because you have a repetition of each cell coordinate, which is not possible. Now, since this is an structure grid, we are able to do so with more accuracy. I'll show you an example. So we have here different folded. We have here the fold axis related to it. And here is one example how we can accurately model using Depogrid the folds features, the trusted folds, and be able to have the linear folds preserved, the geological feature preserved, and be able to simulate it accordingly. One very nice thing, and this is the difference, is we are able to preserve the full fold plane, and the pillars are orthogonal to the surface we are modeling, not to the folds that we are creating. So this allows us to have flexibility to model complex structures the same way we have here. Another example is from the extensional regimes, when we have seen the normal folds that we have here. So we have the different folds and the movement of a channels. For example, if you consider this a channel, you can see the movement of those. If you don't have data, how are you able to preserve the full or the exact movement and the real location of the channel across the fold? The Depo space will allow you to preserve this integrity and this continuity across the folds. And we have examples that we can see that for very complex extension regime with X type of folds, normal folds, the Depogrid allows us to be able to model each compartment of it, keeping the correct fold planes, and be able to have the main depositional feature preserved. And you can see the cells of the folds are cutted. So when I'm modeling the properties, I model it linear, and then it moves up and down. So I'm sure and have more certainty of the continuity across the folds. I'm able to represent the folds, and I have the pillars which are not aligned or directly linked to the fold plane, but linked and aligned and orthogonal to the depositional surface. So that means more geological integrity and fidelity as well. And here is one example. So today we are able to model complex structural basins with extension regimes with complex folds and events like this one I'm showing, without having to have without having pillar grading challenge, and be able to simulate it at the same time accordingly using intercept. Because Depogrid allows us to handle all these complex compressional or stationary regime feature, and account for all the cells angles and all the structural grid complexity, because it is handled as a structural grid. Okay. The next one I would want to show you are the stratigraphy challenge. The same one I was telling before. For example, if you have crossbed, or if we have complex sequence stratigraphy features. And here you can see, so we would define different cross sections, and through the different cross sections, we can define and model those without having to worry with pillars. And here we have an example. So we have different sequence of deposition, and we have different pillars, which will be allows us to account for its complexity across it. I'll show you a more detailed example. Look to this sequence stratigraphy complex model. Imagine if your reservoir has these geological features, and is varying from sand channels silt stones, and mudstones, which will lead you to very complex connectivity channels and areas that you have in. How are you able to model this without having complexity and problems with your grid? If using pillar grid, as we have here an example on the right-hand side, we're able to model your sequence events, but in these zones, you start having problems with your grid cells because they have to connect back to the pillars. You won't have the normal unlapping feature as we would expect. You have infinite small cells, which later will give us problems in conversion. Even though we may reduce the pore volume for these small cells, this is what we reservoir engineers sometimes do. But remember that connectivity in the reservoir, it has big impact. And this sometimes allows us to not represent the real connectivity we have in a reservoir. Looking at the same time on the downlapping side. Now, the Depogrid will allow us to, for each sequence of deposition, we'll have a pillar grid which will align to its deposition feature. And through that, I'm able to honor with accuracy, with less cells, how this complex stratigraph feature that we may have in a grid. Since this is how unstructured, I'm able to model and simulate it in a short period of time with less conversion challenge. So here's just an example where we are seeing porosity, which is magenta, so it's 0, where we have out the magenta color, and this is a grid initial pressure. And through time, as we simulate it, we are able to keep with more confidence areas that will have the high pressure drop and the low pressure drop aligned with the main deposition features and preserve it. Okay, so this is very important because we are seeing that connectivity across different sequences happens, and if we are not able to better model this area, so then we will have a lot of bypass oil, and we will not be able to account for water channeling that happens very fast. So it's crucial we are modeling this area, and this is an example of how Depogrid can allow us to do that with more accuracy. How do we simulate Depogrid? Is there anything very specific to do a simulation of the Depogrid model? And my answer is no. So you simulate it using exactly the same workflow we use with normal pillar grid, with normal VBM type of grid, and the same workflow on the reservoir engineer side. So it's all the same. What we have to do is just to add in the new grid properties and simulate it. So we're able to do that and handle black oil and compositional models. And we're able to model that the same way you do it, running in a cluster, running in your local machine. So nothing changed. The workflow is the same. Basically, what will change is you will be using a Depo grid rather than a pillar grid or a stair-step grid, as I was mentioning before. So same workflow for the reservoir engineer simulation. Look into the reservoir engineer domain. What are the main benefits the Depogrid will bring? And one of them is we have cut cells. So that means if this was an orthogonal grid, normally we would have a lot of conversion challenge. But since this is handled as a structured grid, polyhedral bisector structured grid, so that is removed. So that means we are able to keep the full geological structure. We're able to preserve the volumes in place. We don't need to use much of minimal pore volume. I'll show you in the next slide. And we're able to simulate it at the same time. One very important thing to mention is the pillars are always orthogonal to the base surface. And this also is very good for us when we're handling the vertical permeability challenge that we may occur in a grid. Okay. Through that, we're able to model complex these fault systems without having challenge in the simulation part. The other one is the fidelity, and this is important. So we're able to model different compartments, fault compartments. And if you have a VBM grid, for example, you have here zigzag according to the faults. If you have a pillar grading, you have here the pillars defined. But how do we characterize, how do we handle the cells in an structural grid? So, and here we have what I was saying. The Depogrid has the UVW coordinate system, which if we try to translate to the IJK, we have a specific IJK cell ID, but not unique. And this is the challenge. So if I try to use an IJK used for visualization or filtering of my cell, I may have more than one cell being filtered. And why is that? This is because the cell was cut after we have moved from the Depo space. Before it was one single cell, and then due to the faulting, this cell was cut and it was moved up and down. So if I look to the normal coordinate IJK, these cells have the same ID. So the Depogrid now will have a specific unique cell ID. So each cell will have a specific ID, which will allow us to identify the specific cell. So in this example, you have two cells with the same with the same IJK. They belong in different segments. One could be one side of the fault, one on the other, and they have unique cell ID. And this is what will be passed to the simulation interset, and he'll be able to handle that as an structural grid. Also, being able to have the pillars orthogonal to our surface allows us to handle a lot of the simulation challenges sometimes we may have. And especially when we look into transmissibility computation. And here we use normally the DPFA approximation, which is two-polynomial formation approximation method. If yes, and here is an example in the bottom. So if we have a stair-step grid and we have a fault, how is a well being drilled parallel to this fault? How well can we represent the model? In a zigzag, in a stair-step grid, where we have a grid like this, it's challenging to represent and model the fault and the well flow. If you have a pillar grading, we have the pillars being parallel to the faults, because we need to define the pillars aligned with the fault that we have in. If we have the Depogrid, we have our pillars aligned with our deposition feature. So this is more representative when it comes with the flow, especially permeability, which is directional, vertical or horizontal, and aligned with the deposition feature. So this will allow us to better represent the flow across the bed. And we have here examples of that. And this allows us to better model conings of the water flooding if you have. And here is another example of the value of the orthogonality of the vertical direction and how it allows us to reduce CPU time if we're able to have it modeled with accuracy. Okay. Now, sometimes we say, oh, if we have cells that are pinching out, we can normally just use minimum per volume, reduce them, and we're able to simulate it. So that is true, although that will not allow us to represent some complex connectivity dynamic, the same one I showed in the previous feature. So in the Depogrid, what will happen is we're able to better model all the pinch out features we have in the main unconformity surface, if that is the case. We're able to have different pillars according to the deposition feature, comparing what we have here in the pillar grading. Okay, and we have done a sensitivity analysis just to see if we reduce the minimum per volume in the Depogrid, what is the value? So there is a small variation on the simulation time less, but looking to the saturation, pressure, there is no much impact. So we don't need to do per volume reduction in the Depogrid. So this is a value we add in if we are simulating with Depogrid. So no minimal per volume cutoff required. Now here is just a summary to show you on the reservoir engineer side. Being a structure, we're able to model the faults accurately, and having the pillars orthogonal with the position feature allows us to better represent the vertical dynamics of our reservoir. And with the Depogrid, we're able to model the complex features, the faults being cutted and modeled. We are aligned with simulation. And the main cell ID is different since it's a structural grid. So each cell will have a unique ID, which should be then characterized and move into the simulation part. Also, this allows us to better represent complex features and well locations. Transmissibility is handled by two-point flux approximation, and the connective values functions are taken care. One very important thing, minimum per volume, so and pinch outs don't have much impact when we are simulating with the Depogrid. To finalize, I'd like to show you this quick video just to show you the enhance of the fidelity we have within Depogrid. So here we have two grids representing the complex sequence stratigraph feature I was mentioning. On the left, you have pillar grading model. On the right, you have the Depogrid model. And you can see how you can better model each sequence of deposition, honoring its bed and its variation, the downlapping, not having cells that can create convergence issues that when you are simulating. Here we are seeing the pressure regime of a model. So this is zones of high pressure and low pressure. You can see the integrity of the grid, especially connected with the well. So those are areas where we have high convergence problems when you're simulating. And here you can see you easily can better simulate this well. Okay, adding new wells across specific layers can actually be easily modeled. And here you can see the pressure variation across. So Depogrid allows us to mimic with accuracy the pressure regime and know if we have connectivity or not across the features, which the pillar grading, if we are not able to preserve the deposition of feature, like we do in the Depo space, we may not miss this area that has connectivity or not. Okay, so that is the value of better represent the geology, both the deposition of feature and its structure using I'm using the Depogrid workflow when you have complex features like that. And this also allows us then, when we are modeling, to better manage our strategies of development. Because then we'll better see that our reservoir is not that very well connected, as far as I was thinking before, and I will need a better location for injector to be able to better support it. Okay, here is an example of adding a water injector to be able to support the areas that are connected to my wells. Okay, so this is an additional value of having fidelity to the grid, of not having a grid that allow you to model these complex features, and at the same time allow you to simulate easily, which we can do today using Intersect. In summary, Depogrid is available today in Petrel from 2018 version beyond. It allows you to handle a lot of challenge. Is a structural grid, has its pillars orthogonal. We're able to use uncertainty workflow within the Depogrid. There's been additional features added, so we can use it today within a fractal dual porosity, dual permeability grids. And the only simulator today that is able to handle these unstructured grids is Interset and can easily be molded and being simulated with Interset, which was built for this. So with that, I will finish my presentation. I hope you are following me, you are with me, and I will pass to Samuel, which will give us a demo on how Depogrid works. Samuel, please.
Thank you, Enio. So let me just share my screen.
Yeah, just a question while he's trying to set up. Please, do you have an example of where you have used this in Nigeria?
Hi, thank you. Thank you for the question. So an example, a case study in Nigeria, I need to check. Okay, I don't know by head right now. Although I'll look to our internal communication and get back to you. We have a lot of case studies done globally, many SP papers where you can find in the use of Depogrid in different complex features, but a specific case from Nigeria or public, I do not have or I cannot tell you.
Okay, thank you.
Yes.
Good afternoon, everyone. Thanks, Enio, for that presentation. So I would like to bring home to you what Enio has been presenting using this demo. And to achieve this, I've put together a scenario. So I want you to just imagine that you are part of the asset team and your asset has just adopted Depogrid as the gridding solution to model one of your assets, a part of the Gulf Axe field, which is structurally and stratigraphically complex. So as a result of this, your geologist has actually created a preliminary structural model for this reservoir, which will serve as a basis for building the Depogrid. The structural model contains 23 low defaults, 6 zones, and of course, it has the base Cretaceous or conformity as the uppermost horizon, which we will see. So your objective is to work with your geomodeler to generate the Depogrid from this structural model, that is the VBM. So the structural model has been created already, but I will show you all the steps taken in creating that structural model. Then from the structural model, we will create the Depogrid, and we'll do a quick evaluation of the performance in the downstream simulation workflow by comparing the simulation result of your existing pillar grid to the new Depogrid. You will learn about a VBM, that is a volume-based model, and how to create it. Then you will also learn the quality of the structural model and the Depogrid. And in addition to that, you will explore the key flow-related characteristics of the Depogrid, as well as learning how to QC this gridding option by the way of comparison with QC matrices. And finally, you will learn how Intercept simulates a Depogrid. So you will create a simulation case in Intercept. I've divided this demo into 3 parts. The first is to create the demo grid from the structural model, that's from the VBM. And the second demo will be on how to QC these gridding options. And lastly, I will run you through how to really run the simulation with this Depogrid and compare the results with the existing pillar grid that you've got for this model. So what I'm going to do, I'll just show you the workflow. Let's open a 3D window just for visualization to display some of the modules that we already have. Like the pillar grid is a complete module that you've been using previously in your company. So now we want to move to the Depogrid. So, but we can view the property just for us to see. So that pillar grid has been created from the 4th module that you see there that defines the fault framework or the structural framework for it. So now I'm displaying the porosity. Let's try to scale the column just to make it more appealing. If you remove the filter, the J slice filter, you can see the entire model. So that is that for the pillar grid. It has all the properties that you require for your simulation. You can also see the structural framework that has been built and the structural model that was built on that framework. And the same structural model has been used to create the stair-step grid, which is what we're looking at now. The last type of grid that we're planning to create now is Depogrid on the same basis of the structural framework that you've got there. So I'm going to take you through step by step on how it is being done. The first thing is to create the structural framework. And creating the structural framework is just to make a decision on what will be the domain, time domain or depth domain that you're going to be working on. Next is to create the fault framework. So in creating the fault framework, we require the input interpreted faults. So which is what we're going to, from the seismic, all the fault that has been interpreted directly from the seismic. So you can see that under the seismic folder in the input pane, and you can display them if you want to visualize them, and drop all of them in this process. So this process will use some of these methods that you see, like convex OR, to create the geometry of the modeled faults from the interpreted faults, right? We also define the relationship that may exist between these faults. Maybe some of them are truncating on another one. Which one is the major one? Which one is the minor one? So you define the relationship here, basically. And from that relationship, the outcome of this process is to give you the fault framework. So you are moving from the interpreted faults to the fault framework, which will be used for the our structural model. And you can display the fault framework that you've got. So you need to remember that this is actually, the framework is a triangular mesh representation of the interpreted faults, intercepted and wedded into a framework. And that forms the basis of our structural model. And we can see that by displaying the mesh. So you can see those triangular meshes that Ennio talked about, how the cells has been created, particularly along the boundary or the fault planes. So let's move on to the next step in this workflow, which is to create the model boundary. So you might use polygon to define the boundary of your model, or you can just use a rectangular box. You also need to define the vertical boundary, which can also be based on your fault framework, or you specify what is the height and what is the base. And now we can display the empty bounding box that we have created. So the next in the workflow is actually to create a model to do model construction. So what the model construction would do is to define the stratigraphy of the model based on the horizon interpretations and the welltop adjustments that we want to make to those horizons. So this is the welltops as the input, and this is the horizons. And the outcome is in an unrefined state. So you just tie different horizons. So the vertical definition is just based on the actual horizons that you've got and being adjusted to your welltops that you have as well. So the generated horizons give an approximate fit to the data that you've got. But in the model refinement step, those unrefined horizons are remeshed to a higher resolution and moved to better match the input point data. And so if you notice here, let's say we're using 100 meters as the resolution that we are specifying, which is the average edge length of the triangular mesh representing the horizons, okay? So, and that will create your zones. The final process gives you the zones from here. So if you take out the overboarding, underboarding from there, you can actually see the actual model that you've got. One thing that you might want to do, let's take out the fault framework so you can see the horizons that has been created now clearly. And another thing that might be of interest is to actually take out the zones. Let's take out the zone. Let's display the fourth module, and let's display one of the horizons that was previously created. Let's say tablet 2. So you can best view the underlying mesh structure by actually viewing it in the hidden line view, which you have seen. You can see how those faults and the horizons, they are connected, the polyhedral shape. So the next in the workflow is depot space calculation. I'm just going to pause to give you the overview of what we're trying to do here. Annie already explained the concept behind it, which is great. So we're just trying to reconstruct the horizons so that they go back to the undeformed state. Basically, we're transforming from the geospace, that is the space that you already have impact of the tectonics on your structure, to the depot space when you take that away. So you flatten the structure by removing the impact of the faults and deformations. And in this case, we're trying to use a mechanical flattening techniques. So you create the relationship basically between the geospace and the depot space, that's the undeformed one. And that is why at the end of this process, you will be able to switch between geospace and the depot space and check your module or your horizon accordingly. But the main benefit of this is it really helps it with the property population, because if you imagine that you have a reverse faulting system or you are in a reverse faulting environment, then you may have repeated layers of the structure which will affect the property population algorithm. You might populate the property wrongly. That is the first problem. Or you could even have more layers than the actual, which are not geologically consistent. And that is the main problem that we have been dealing with pillar grid ever. But with the Depogrid, this problem has now been completely eliminated. And if you look at what is going on here, I'm just showing you that I'm not going to include the impact of I'm excluding overburden and underburden. And when you finally finish with this process and you click OK, or what you're going to have is it gives you this view that you can switch. So, and let's take out the fault again and the horizon. Let's just put our zone so you can see the zone. Let's remove, if you want, the overburden because we didn't include it and the overburden. And this is what we've got. So what we're going to do with this is to now switch between the geospace. This is the geospace view, the one that has been affected, deformed. So let's look at it in the depot space so you can see where it has flattened out. And like I said, this is the one. When you are doing property population, it uses this, and that eliminates all the challenges that we've been having previously with the pillar grid from this process. And after the property populations, you can now use your module in a geospace for the subsequent analysis. So the last part of this workflow is to create the structural grid, that is Depogrid, from the structural model that we have created. So let's call the name of the grid Depogrid, and let's drop our structural model now into here. And so notice that at this level, you can define the layers that you want. And the gridding technique currently is the stair-step fault. So we can change to Depogrid and define the layers within each stratigraphic zones that has been created under the model refinement. So let's say the first zone will be 15 layers, and let's say the second zone will be 5 layers, and the next zone will be subdivided into 8 layers, and next, let's say 6 layers. And so we're defining the resolutions with respect to the layers of each zone. And the next one, let's say 15 layers. So, and let's say, okay, that will create the grid. Maybe we can just move it under the structural framework that has been used Just bring it down a little bit. Yeah, fantastic. So what we notice here is that we have pre-calculated properties like the cell index and the region fault blocks with the generation of this grid. So the cell index is very useful in the sense that it gives unique identity to each cell. Remember, Enio mentioned that there is no notion of IJK in the Depogrid because it's strictly unstructured. Even though we have the virtual IJK for slicing and filtering of the module, if you want to slice or you want to filter the module. But this is not unique because some cells have the same IJK value, or if you like, you can call it UVW nomenclature, because they are cut cells. They are cut cells because of the fault that has gone through that cell has been splitted into 2 or 3. All these 2 or 3 cells will end up having the same IJK value. And that is why the IJK value is not unique. But the cell index gives that uniqueness that we require. Okay, let's look at this now. We can look at the region fault block. It's also one of the pre-calculated properties with the Depogrid when you create a Depogrid. But what I want to do, let's go to the property tab, and under the property modeling group, let's open the geometrical modeling. And let's try to generate now a new property called the cut cell index. So what the cut cell index would do, which is really interesting, is that it helps to see the state of each cell in the module. If a cell is not cut, its value is 0. If a cell is cut, its value is equal to the number of parts of the original cell that has been split into. Let's remove this particular top layer so that we can see clearly. We can see that almost 70% of the cell has not been cut. And so they have regular keyboard because they are far from the boundary or from the fault. Whereas we have about 12% of the cells that are cut but has not been splitted, so they will have the value of 1. And those that have 2 or more, they mean that that's the number that each cell has been splitted into. So those cells that have been splitted, they will have the same value. Let me use the index filter to illustrate that for you. Let's filter a single cell, let's say 14 to 14, using the index filter. Let's say on the J, we want 28 to 28. And lastly, on the K, let's say we want maybe 21 to 21. So this is, in principle, this is a single cell. But what you will notice here, if you click on OK, and if you zoom that out, you're going to see that you actually have 2 cells with the same IJK value. And if you try to see what has happened, one fault has actually splitted this. Let's try to locate that fault and display it. The fault is the boundary fault west. So let's put the boundary fault west here, and that will help you to see what has happened. That cell has been splitted as a result of the fault that cut across cell. So here, and you can also look at through the inspector, you see they have the same IJK value but different cell index value, and that is what is unique to each of them. So display the grid using face instead of the cell as the outline, so that you can see the polyhedra that is used for those cells. You can see how complex, but that is really define the geometry of the cells. This brings us to the end of the first demo. So the next is to go and QC the grid that we have created. So there are several QC indexes that we can use to quality check this grid. So I will focus on a few of them in this demo. We have compaction and dilation ratio. So the ratio of the length of the cell in the geospace to the length of the cell in the depot space. We also have relative rotation angle or orthogonality angle. We also have the cell dimensions and cell volume. So I'm just going to create a few of them in this demo. So let's start from where we stopped. So now I'm going to reset the filter. So go back to the filter. Let's remove the filter. You can just go to use index filter and take it out and click on OK. So now you see all the cells in the module, and you can see what has happened along those boundaries and those fault planes, actually, how those cells have been really defined with those the polyhedra. So the first property, I want to create another property with the geometrical modeling too. So let's create cell width, because cell width will help you to see the dimension of each cell. And this is really interesting when you look at this. Notice that away from the fault or the boundary, the Depogrid cells are uniformly sized. But along the fault plane, then they have to really define them to make sure that they capture this complexity that may exist. The next that I want to create is the cell angle. Will help to understand the deviation of each cell from the requirement of the orthogonality. If you just display the cell angle, you see everything seems to be almost uniform. We can do something, let's filter, because what we normally do is to accept the deviation below a certain threshold. Let's say 25 cell angle and above would not be considered as good cells for the simulation combined. But it looks pretty good because we don't see much of that. It will be interesting to also compare the equivalent the cell angle in the pillar grid. So let's go to the pillar grid and display the cell angle property that has been computed. Then we can just compare the two of them together. So what I'm trying to do now is just to link the two windows together. But before you can link the two windows together, you need to go to the window layout. So this is my window layout. You tie them down together side by side. Let's also remove the IJK slice. I guess what will be interesting is we make sure that we view the same layer, link them together. You can see that this is showing high cell angles. So maybe what we can do is to apply filter. Let me take the mesh out from there. So you can look at both of them. And it's also interesting to see that along the boundary, you see those zigzag definition, unlike the actual geometry of the model, which we see in the pillar, in the Depogrid. Display all the cells and make sure there is no filter again. Now, what I'm going to do is to just create a filter on the 1D filter on the cell angle for the pillar grid module. Let's use the same 25 and above. And you can see so many cells that are deviated along those boundaries. These are potential cells that will create problems for the simulation. And if you look at the Depogrid, it's nothing. This shows another value of the Depogrid. So this is the kind of grid that you want to embrace in your workflow because it gives a more representation of your reservoir than in terms of the geological features, stratigraphic features, structural features, and it also helps significantly with the population of the properties because it's doing that, taking it behind the scene to the depot space to make sure that there are no inconsistencies of layers if you have a reverse fault environment. So what I want to do, instead of going to property population, the conventional one that we have to use the log, I want to move, since they are the same number of cells, everything, I want to move the property to the equivalent cell in the Depogrid from the pillar grid. So I'm moving those properties that we need. At least we're sure then that we're comparing apple for apple in terms of the grid. The geometry definition, the same layers are the same. And I'm moving the property now directly. That is why I'm using a cell center approach. So now, once that is ready, then we are ready to run the simulation and compare the results. So this is going on now. It's creating them. The properties are ready. And one thing that I want to point out here is you can also use calculator the same way we usually use the calculator, right? It doesn't make, it's the same grid. I mean, of course, you can see those properties. And there is something very interesting here. Look at the outcrop, how the outcrop, if you display the fluvial facie, you can really see, which is really powerful. If you put this side by side with the pillar grid one, let's link the two screens together so you can see more geological details. We have all the property moved. I'm just going to skip through this because of time so that I can show you this is where I mentioned that if you want to, for instance, use calculator and just overwrite in times Z just to let you see, because that's the original value anyway. It's just 0.1 of the lateral permeability that we used previously. And that is the end of that. So the last one is the volume calculation and the simulation part. So we're just going to continue from where we stopped. So what we're going to do now is we want to do a quick volume comparison during the volume calculation. But before I do the volume calculation, I just want to enter my contacts. That is I don't have the gas oil contact here, but I have the oil water contacts. So what I'm doing there now is putting the oil water contact into it. Now we've created the contacts and we can just go to the volume calculation now. You can create a new case from the pillar grid case so that all the properties can just be retained. So just give it a new name and say it's a Depo volume or whatever you want to call it, feel free. Then remember to change the grid to the Depo grid, right? That's the only thing that you need to do. And you need to drop the oil water contact. But if you have used the same name, it will automatically pick it up from the Depo grid. But because I didn't change the name, that's why we have to drop it. Every other stuff are the same, the porosity, all this is is from the pillar grid. So you can apply and run the volume calculation. And based on the volume calculation, you can now compare the volume. You can look at the STOIP, for instance, in both of them. And you will realize that one is obviously overestimating. This is coming from the Depo grid. And if you just say, you can see the STOIP, 165, you can see the pore volume. But because of the fault plane that is not correctly defined in the pillar grid, that will impact this value. Remember, we're using the same porosity because we moved the property from the pillar grid. But you can see the value, 292 and 169. So sometimes having a good representation of your grid also will definitely impact your volume, because from the volume calculation, grid porosity, there are all the parameters that are needed for the volume calculation. Okay, so the next thing that I want to show you here for the simulation is just to show you that in the pillar grid, we have two faults that are sealing. So I just want to show you that you can also apply the same multiplier to the Depo grid. So let's go to the Depo grid and the same two faults. We need to create the multiplier for it. So that's the Depo grid. Just highlight it, go to assign multiplier. And all you need to do here is just to locate those two faults and also put them. Apart from that, every other thing is the same in this module. And I'm just going to change that to sealing those two faults. That's one of them. Main fault, north-south. So it's sealing. The next one is NNESSW, which I'm going to make also sealing. So once we change the grid, everything should be okay. But now we're using the properties from the Depo grid here. So let's give it a name so that you see it's a very simple step. Then we'll run it and compare the result. And so, I mean, whether you use Depo grid or you use pillar grid, it makes, in terms of the workflow, it doesn't make any difference. But you gain a lot of benefits that we've been talking about. The fidelity of the module is honored, and the result is definitely more accurate. So now we have Depo grid, apply it, and I'm going to run it, and it's going to run pretty fast as compared to the pillar grid. So now we say run. Now I set the project, and I just need to rerun it quickly. The simulation is done. I'm just going to compare the pillar grid and the Depo grid. So this is the field. I'm selecting the case pillar grid. I'm creating a chart for field responses. So I'm going to select the pressure for the field. You can already see the difference in the results. And I want to gas and the water. Then I want to split it by property so that you can see what is going on clearly. And you can see at the field level, it makes a difference. So sometimes we struggle even in history matching, but the problem is with the grid definition that we have used, right? Let's take an example of a well level comparison. I'm going to change to the add another chart to my study by creating a well. And let's take the two cases again to compare. If you like, you can compare with the stair step that we've created, but I'm just interested in showing you these two quickly. Bottom up pressure of these two wells, of this particular well rather. And let's put the oil production, gas production. Then let's also split by property just to see what is going on. If you've done the gas production, you will have been able to see better. So we're just going to do a split now. Yeah, that's for well A. I just want to make sure it's only one well that is there. Then split the property and you can see basically what is going on. And if you want to actually to see the result very well, because right now the rates graph will use the same the same range. So I don't want that to happen so that you can see more clearly what is going on. I wanted to use gas production there. You will have seen the difference there again. The reason why there is no difference on the oil rate is because the control is on the oil rate. So the last thing that I want to show you the location of that well. And you can see how close it is to this spot. And those disparities in the results is because of the pillar grid actually, because if you look at the pillar grid, it crosses wrongly because of the geometry of the representation. And that is what, changed completely the dynamics of the model. So thank you so much. That's the end of the workflow that I want to show you. I just want to say, we promise that we're going to share with you all the videos and for all the sections that we've been delivering and those that we deliver. We're currently in the process to do that. We're hoping that we should be able to get them out to you before this one, but we will really prioritize it this week and get it across to you as soon as possible. We'll also send you a feedback link. Please, we need your feedback. We really appreciate if you can spend time. It's less than 5 minutes just to give the feedback on all the sections that we have delivered. And with that will be the end from my side. I'm not sure if anyone wants to ask something to it. Yeah, or if you have questions.
Thank you very much, Sam. So we are open to questions. If you have any question, please just raise your hand. There is no questions in the chat window. Although, please raise your hand and or unmute yourself. Yes, please, Ikon Okonkwo.
Okay.
Please unmute yourself. Yeah.
Okay, thank you very much. I actually enjoyed the presentation. The quick comment I have, although I'll still do my feedback, is it possible to do these sessions 12 to 1? Because really it clashes with a lot of meetings that we have within the company, and I just struggle most times to really join. Yeah, and then the question I have again is if we already have Petrel license, this intersect and the Depogrid method, is it a feature that will require another license for one to get and start using it?
Mm-hmm. Okay, thank you very much. So, Sam, can I go ahead or you?
Oh, yeah, that's fine. You can go ahead.
Yeah, thank you. So the first question regarding the meet time. So we are trying to accommodate people across different countries with different time zones from the East Africa and the West Africa. and this the time that are actually manageable to each one. Although in the survey, if everyone can put their suggested time as we send out, we are able to align it and then propose a better time that may suit everyone. So we work on that with everyone to see if we can adjust to a more suitable time that allows to have more participation on this technical session. So regarding the Petrel, so if you have Petrel license, Petrel ARI, and especially Petrel combined core or Petrel GEG, so you can use and build your Depogrid models. So it is a geological feature. So if you have a Petrel GEG combined core, you can use it and build your Depogrid. What is different is the intercept. So the simulator requires a separate license from Petrel. So you need one license for Petrel and one license for intercept in order to run the model.
Okay, thank you.
Yeah. Any other questions?
There's a question for Nelson. Nelson, please. Can you unmute?
Mine is not really a question. The challenge that we have most time. Can you hear me?
Yes. Nelson,
Okay.
go ahead.
The challenge that we have is that I don't know of other people, but most time we don't build the static model. So I don't know if it's something that, as reservoir engineers, we can easily build on our own, because most time is the static model is being given to us by G&G guys. Then we start from, where they stop.
Okay, so next thing, the expectation of this section is not to promote engineers to be building structural grid. Okay, yeah. We're just trying to show the understanding and the values. And that was why, if you notice, we sent an email that if you can invite the people in your geomodeling team to join, that it will be helpful. So the main benefit for you is just to encourage them. You want to let them use Depogrid, especially if you have very complex geology and you are struggling with pillar grid. And this is a good opportunity now for you as a reservoir engineer. Yeah.
What I'm even saying, I think you have contact of all of them, so I'm thinking that you should invite them to this section too, so that they can understand the importance of building, this model in Depogrid, because just like what you've demonstrated, you've seen that it has impact in even the history matching and the results we get at the end of the day. So it would be good if they are also aware, so that by the time we are letting them know, you understand, they will know the reason why we are insisting that they should use Depogrid.
Please, Nelson, help us to put that on your feedback, this section, and we have to look for a way to run a similar one with the geomodeling team. I'm sure our G&G team too. Bayo was in the call before, but we will get the feedback across to him so that they can run a proper section on the structural modeling for the geomodeler.
Okay. Thank you very much.
You're welcome.
And
Mr.
just to add, yes, please.
Okay, yeah, thank you, Henio, thank you, Samuel, for that wonderful presentation. And honestly, I think it's very clear, especially with those the two applications we talked about. The Depogrid and using intersect, but my question is, within Schlumberger, within your development, what do you call it? Is it not possible to find a way for Eclipse to handle this thing? Because what I see here is that it's not just enough to have Depogrid and build. You must also have the finesse to use intersect, and of course, that's another ball game too. Because what it means is, I don't know whether you people plan that in future to rest Eclipse, because the whole essence, I think, is as much as possible if we can capture most of how things are reality, I mean, I think the better. And I can see that Depogrid is a wonderful technology. And then plus this intersect. So, but my question is it not possible that your software developers find a way such that this can be handled in Eclipse?
Okay.
Because what this means for us, for my company, would be, okay, I think we begin to make a case for intersect and then get the trainings, and then the next thing is why should I go back to Eclipse if I find something that can do better? Thank you.
Elliot, do you want me to take that?
Okay, Sam. Go ahead, and then I add on. Yeah.
Yeah, sure. So thank you so much for that. One thing about this is if you have our way, we will make Eclipse to do it from the beginning without even any issue. But the formulation of Eclipse would not allow that. The architecture would never support it. Like we mentioned, this is unstructured grid. Depogrid is unstructured, and that is why we're able to capture accurately all these complexities. We cannot do that with the regular structured grid. And since Eclipse is not designed for unstructured grid, that will be the only reason why it will not be possible. Again, you need to also remember that we're now talking about next-gen simulator. Intercept is the next-gen simulator. And the purpose of the next-gen simulator is a simulator that can actually handle very complex problems, handle the fidelity of the module, retaining the physics, because things are getting now complicated. So we want to, the risk level, we want to keep it as low as possible. And that is why accuracy is key. Fidelity is key. Physics is key. Performance is key. And that is what the new generational simulator is bringing to the market, Intercept. So just to answer your question, I don't see that it will not happen with Eclipse. Unfortunately, if I've disappointed you, I'm sorry about that. But that is the reality.
Okay, that's fine.
Thank you for the question, Mr. Caviro. Just to add to what someone said, that beyond all the complexity we want to have model with accuracy and the simulator, there is also the evolution of the code and the new challenge that Intercept brings. So, and this actually, and you see in the next section as we go to the Intercept modeling, is the direction the industry through time will go to. And there are multiple ways you can later upgrade your Eclipse to Intercept. So, and you won't have to change anything. You won't have to start from zero or rebuild again. So you have everything in Petrel. You were able to easily move from one to the other, and you have more clarity on this in the next session as we will show you the Intercept. So it will be a smooth transition pathway in terms of you as a user using Petrel and the simulator. So, but we are moving to the future. We are moving to the digital, and through time, as complexities and challenges become heavier, as someone just explained, this is where this simulation is required. And this is one example where Intercept is the only simulator in the market that can handle the unstructured grids through Petrel. For now.
Okay, thank you.
Maybe because of our time, we can take other questions offline. We just want to thank everyone for making our time to participate in this presentation. Like we promised, we're working hard to make sure you get all the videos or the links to the videos so that you can watch it whenever you need the knowledge that you've been accumulating via these sections. The member will also send the feedback. Please help us to provide the feedback. And we look forward to see you in the next section. Do you want to show the slide for the next section? Close the...
Exactly.
Okay. I will stop sharing.
All right, so we, to finish, our next session will be on Delphi workflow. So we will show you and present you a little bit on our digital landscape on the reservoir engineer side. And you see how all this value we present before can be enhanced and improve further using our digital solutions to help. So this will be our next session. We count with your presence, and thank you very much. Stay safe, and we meet again next week.
Thank you, guys.
Yeah, thank you.
Thank you.
Thank you.
Thank you very much.
Bye.
Thank you very much, everyone.